welcome once again to RF transceiver design course. We are discussing about transceiver architecture. We left at the RC polyphase filter discussion. One more thing I want to add in the RC polyphase filter, that we can also make a cascaded polyphase section, and what will happen that you can make a same output again connected to input, and we need to rotate it. So, here it is a rotated one. So, this is a first section, and then there is a rotated section, again the output of one will be given to input to the other, and that widely it is mentioned like this. This is a stage 1, this is a stage 2, stage 3, stage 4. And what is the advantage of this? In simple, if we consider only R1 C1, it has a very limited bandwidth. However, we can improve the bandwidth of the rejection by adding the cascaded stage, but it has also some disadvantage. If there are more variation in the R and C, then there is a possibility that you have your image rejection ratio throughout the band will not be constant, and there is a loading, means because there are more RC, there is a loading effect is also going to come. So, that you need to consider while designing a multiple stage polyphase filters. This will here we are concluding for the polyphase filter, and that are the all the image reject receiver we have discussed. Now, there is a one more thing, you can also use you can also add the 90-degree phase shift prior to the doing after the down conversion at the input side. But we generally avoid this, because at the input side if we try to add the RC, it is possible that your noise will increase and you can not get sufficient phase change at very high frequency. But there are certain application where let us say you can use a quadrature hybrid couplers by using inductor and capacitors, which will provide you 0 and 90-degree phase shift at the RF end. Then you can use this kind of architecture where you convert the RF signal to 0 and 90, and then you just use apply sin omega L or cos omega L t, and this is how you can do the image rejection. There is another way also, which is the simplest way. If you do not want to implement RC filter, just directly you convert the sine and cosine signal in ADC, convert to the digital, and then again on the digital domain you add the 90-degree phase shift and then add. So, this is how. So, here also ADC, or there is a quadrature ADC that can be used, and the complete down conversion you will do and the digital domain. So, where it is easy to add the 90-degree phase shift in digital domain. So, in many applications that on digital side also people has tried to do in the literature. So, these are the two alternative way we can also add the 90-degree phase shift. There is a digital IF. So, in some of the literature it is called as a digital IF, where mostly the baseband after the down conversion IF filter entire ADC has been used, and then you have a channel selection which is a reconfigurable. So, that can be software defined. So, you can easily do the image rejection and the band selection, but channel selection. So, entire band will be converted to the digital, and then in digital we will select the channel instead of using a channel select filter. However, in this case you required a ADC with very high resolution, and it dynamic range should be high. It requires many bits, but there is a flexibility in terms of the reconfigurability. You can easily select the channel. So, it is called a It is named as a digital IF because you are adding the reconfigurability at the baseband. Even there are some receiver architecture for mostly for radar application has been tried, where after the LNA direct ADC has been used, and the channel selection and everything, they means even down conversion is also has been done at the digital side. So, this is a special kind of ADC that will also help, this will work at very high carrier frequency, and it will convert to the digital data. So, this is called a digital IF receiver. There is another class of receiver that I have added here, because it was in the century 1914 century, Edwin Armstrong has invented, and it is the first receiver architecture that was employed in the radio, and it is called a regenerative super regenerative receiver architecture. The it is a very simple architecture where positive feedback is used and where your inductor capacitor is attuned. So, this is the paper in which uh, Edwin Armstrong has discussed this architecture. This is referred from that paper, and here due to positive feedback, the moment L and C will tune to the frequency of incoming signal, then you will have the high output voltage. This is a basic block diagram. So, this can be converted into the block diagram where there is an amplifier and feedback that is attuned, and at a tuning frequency this will amplify the signal, and then there is a detector which will in this case it is a speaker. So, in 21st century why I am talking about the super regenerative receiver, because it has also application. If you are going for the let us say biomedical application, or where your RF frequency is in megahertz, there are in certain IoT application also where you do not want to add too much complexity and you want to reduce the power consumption. In that case we can use this architecture, and in some of the biomedical architecture, many papers are published on super regenerative receiver. So, this can also be considered as one of the receiver architecture. It is the advantage is that it is a simple and it can be easily implemented, but the disadvantage is it is involve positive feedback. So, you required a very fine tuning. So, tuning is very important in super regenerative receiver architecture. Then there is impulse radio receiver architecture. So, it is used for short range, low power and high speed application, where very means a pulse of the signal has been sent, and for short range we within a range of 3.1 to 10.6 gigahertz, and what you can do is just use a mixer and envelope detector to down convert the signal. So, it is mostly used where in radar application this kind of impulse radio receiver, where you send a pulse and then try to receive the pulse and find out the distance between the object and the receiver. So, that has a specific, for specific application impulse radio receivers are used, and it has a combination of mixer and correlator. The only the disadvantage of this architecture is you need to have a very wide band 3.1 gigahertz to 10.6 gigahertz. That means your LNA mixer, all the components should work for that entire band, and that will limit the performance of this radio impulse radio receiver. So, let me summarize. We in last 1 or 2 3 classes we have gone through various receiver architecture. If we summarize the receiver architecture, then these are the basic summary you can keep in your mind. So, just now we have considered the super regenerative receiver architecture. The complexity is low. You can also do the full integration is possible. The power consumption is also low, and same thing is applied to impulse radio receiver. It is a complexity low. Full integration is possible. However, no carrier impulse with wide bandwidth can cause interference with other system if emitted power is not limited. So, we need to consider that our emitted power is a limited. High sensitivity because of the resonant feedback, there is a sensitivity is better in super regenerative. However, in impulse there is a high bandwidth of this allows the high data rate. So, very let us say because the wide bandwidth it has a higher data rate. It can provide the high data rate, and you can easily also reconstruct the image, means in the mostly in sensing image and sensing, this kind of impulse radio can be used. Then super heterodyne, we already seen the complexity is moderate. Full integration of chip image reject and channel select filter we need to use. So, there are it is a trade off, it cannot be have a all the chip complete chip solution on the single chip. We have many components need to use the off chip. The power consumption is moderate, and IF has to be trade off in channel selection and image rejection. So, we already seen that we need to consider the IF frequency, so that we can also use channel selection and image rejection both. There is a dual super heterodyne architecture. It is very highly complex. We have seen that the multiple down conversion we are trying to do. It is a full integration is there are off-chip components, that is why it is not possible. Power consumption is very high because you have multiple components and at least 3 or 4 chip solution is there each chip, and you need multiple synthesizers. So, power consumption is very high and good image rejection. So, it has an advantage that it will provide a very good image rejection and channel selection. So, where your mission is very critical and you need your accuracy to be very high, at that time this kind of super heterodyne architectures are used. Now, direct conversion receiver, it has a very low complexity and there is a full integration is possible. The power consumption is low. What are the problem of DC offset? We already have seen problem of direct conversion receiver, that is a DC offset, or it is a sensitive to the flicker noise. But this architecture is also widely used because it is very simple, and on chip the space and size it is taking is too low. The another widely used on chip architecture is a low IF receiver. It is complexity is a low and moderate. Full integration is possible. Power consumption is low and moderate, and overall there is a good performance. And digital IF, RF very low baseband and very high. RF frequency complexity is very low, but for baseband very high, because here I told that ADC required a high dynamic range. So, when we are designing the baseband, the complexity will increase. Full integration is possible. We can also have a high power consumption because of the multiple baseband modules. Very flexible architecture and can handle different standards, modulation and frequency. So, there is a software defined IF. So, that is why we can have a more flexibility in terms of selection and all. However, ADC limits the dynamic range, and which is a major drawback. So, these are all the receiver architecture. Here when we have considered the heterodyne, super heterodyne and dual super heterodyne, in both the case you can also use, so either Hartley architecture or Weaver architecture. All the image reject architecture are a part of heterodyne architecture. Even a low IF you need to reject the image, so that is a heterodyne architecture. And in direct conversion you have a omega RF is equal to omega LO, so it is a directly converted to the baseband. So this is all about the receiver architecture that we have seen, and this entire module will help you to implement any receiver architecture that you want to perform. Now we will move to the transmitter architecture. So the basic difference between receiver and architecture. So when we have considered the receiver, so if this is a omega RF signal and if this is a omega LO signal, so ideally when you multiply these two signal you will get a two term, omega RF minus omega LO and omega RF plus omega LO. So up to now in entire all the receiver architecture we have added a low pass filter here. So what happens, we have tried to reject this frequency, that is omega RF plus omega LO. Now when we are going for the transmitter design, we are not going to use this frequency. Our baseband frequency is less, let us say 100 megahertz, and we want to up convert into the 900 at 2.4 gigahertz or high frequency. So at that time, so this is a receiver, and in transmitter what generally we will do, we will use a mixer. This is a baseband signal, so let us say omega baseband and then omega RF or omega carrier you can say, and you have a omega RF plus omega baseband. And how you will do that, we will use a band pass filter here. So you will get omega RF plus omega baseband. However, transmitter has a advantage of doing multiple thing at the baseband, and then you just do the up conversion. So this is called up conversion. So in receiver we use a down conversion, and in transmitter we use a up conversion. So this is how the transmitter will work. So you can use all receiver architecture that we have discussed in the last 2-3 lectures. The same receiver architecture can be employed in the transmitter. The only change is now we need to consider the up conversion, not the down conversion. And what is another difference, that when we are receiving the signal, LNA is an important component, but when we are doing the transmission, power amplifier, because that is the last component. So this LNA is a RF component and power amplifier is also RF component. So your low noise amplifier here is important, which is connected to the antenna. It should add a low noise and have a higher gain. However, power amplifier, which is a part of transmitter, it should provide a sufficient power so that your signal can travel to the long distance. And another important point is it should also have a sufficient linearity. We have seen in the basic of wireless communication that when we are using a complex modulation scheme like QAM and OFDM, at that time when we are using this kind of modulation, we need our power amplifier should be as linear as possible, so that while we can converting the signal at the receiver side, we can easily reconstruct the data which we have transmitted. So, this is a basic difference in terms of the architecture between the receiver and transmitter. Now, we will see one by one all the transmitter architecture, and we will go through the each components, what are the issues in the transmitter architecture. So, same thing, this is a very basic transmitter architecture which has been drawn here. There is a baseband data, and then there is a address generator which is generating the address. There is a IROM and QROM. So, in baseband you can easily do the I data, means I and Q data you can generate. Then this I and Q ROM will have all the information of the modulation and everything, your data is there. Then you need a digital to analog converter which will convert your digital data to analog, and then that as a that data is a low pass filter and multiply with the cos omega LO t. So, this is and then you will have a modulated output signal. After that you can use a up conversion. So, means here there is a cos omega LO t, sin omega LO t is applied. So, we are using a quadrature modulation, we are adding the signal, and then we need to use a power amplifier. So, this is how the transmitter architecture will work. So, the basic transmitter architecture is a high direct conversion transceiver architecture, where we directly convert the baseband signal to the very high frequency signal at omega LO2. So, if this is a cos omega LO2 and sin omega LO2, if we multiply, this is I data and Q data, it will be added. So, what we will get? I plus j q, and we have seen in the while discussing the Hilbert transform, if you do I plus j q, you will get the e raised to j omega c t, that is a carrier, your signal is then up converted to the carrier frequency, positive carrier frequency omega c t, and then there is a power amplifier which will amplify. Power amplifier has one important component, that is a matching network. So, your output of the power amplifier should be matched with the antenna, or this is a duplexer. We have seen the use of duplexer also. If you want to use the transmission and reception both together, we will use a duplexer. But there is a problem, means the same problem that we have discussed in the direct conversion, that will come in the direct conversion receiver, that will come in the direct conversion transmitter also, that is a IQ mismatch. And if IQ mismatch, it follows that the power of unwanted sideband divided by the wanted sideband is given by. So, what are the unwanted? In when we have seen the image rejection ratio also, that same thing, and when we are discussing the IQ mismatch also, the change in the amplitude. So, 1 plus sigma. So, sigma is a error in the amplitude and delta theta is a error in the phase. So, if when you are applying with cos omega LOT and sin omega LOT, if there is a change in the phase of delta theta, or if there is a change in amplitude of sigma, this is what IQ mismatch you can quantify by using this equation. So, if you do not have the delta theta is 0, means there is no phase difference, then your IQ mismatch is 0. So, there is a you cannot find a sufficient IQ mismatch, but in reality there is a difference between cos phase of cos omega LOT and sin omega LOT, and it will add some IQ mismatch. There is another problem in the RF frequency, that is a carrier leakage. Same we have also discussed in the direct conversion. So, here what will happen, that when you have a cos omega LO2 t and sin omega LO2 t, the some of the portion, if it is power amplifier, and then that has a this carrier, because when we up convert the signal, some of the portion of carrier will go and leakage. So, that will leakage to the receiver, and this leakage is very severe when we are using a direct conversion architecture, because your RF frequency and LO frequency both are same. And then you also need to consider the, if mixer is also non-linear, then it will add the sufficient non-linearity in your entire receiver, entire transmitter architecture. So, we will discuss about more in detail about the all the transmitter architecture in the next class. Thank you, and all other information about the transmitter architecture will be we will discuss in the next class. Thank you all of you.